So here I set the stage for logistic regression, and as I mentioned, has nothing to do with linear regression. It's a classifier, but it makes sense to take a look at what we did in linear regression. Remember, we tried to predict the price of a house of my friend, and basically in function of the size of the house. Yeah? And basically what we did is we looked at 6 comparables, or houses that were sold in the past 1-2 months, and that were in the neighborhood of where my friend's house was. And we tried to fit a line between all these red dots. And we saw that it was not possible to fit a line that connects all the red dots. But we decided to draw the best line, the best possible line, as a model. And the best line had 2 parameters, W and B, which we needed to find. So in order to find the W's, we first decided on a cost function. We used mean square error, and the cost would be the sum of all these little vertical red lines. Because, for example, this dot would be, this dot would be Y, and it's the 3rd sample, Y3 real, whereas this point would be Y3 predicted. Well, the blue point is predicted. There is a distance, and we sum up all these distances. Once we have the cost, we looked at minimizing the cost, because minimizing the cost would give us the best line, and that's how we ended up doing gradient descent. You know, we start somewhere and we walk down the hill until we reach the minimum. And that's how we calculate the parameters W and B. Now we've also seen that there is a multivariate case. It's a univariate, only one variable, x. And we could write this as y predict is wx, w0, x0, all the way down to wd, xd, when we have d features. In this case, you only have size, only one feature. So here, d is 1. Yeah? D is 1. And we also saw that we can get this in a matrix form or in a vector form. And we did, for example, we set x0 to 1. Yeah? And then we have the matrix notation. Yeah, remember, we had an x vector, and the x vector started with 1, and then x1 all the way down to xd, and then w transpose was a bit similar. Sorry, this is a transpose, so this is w0, w1 all the way to wd. Yeah, and if you multiply this, then you get this formula. Yeah. Okay, now something that we did not look at is that basically there is a closed form formula, meaning there's an analytical way to find the W and the B. First of all, we're gonna drop the B here. In worst case, we call it W0. Yeah? So we have only one variable to worry about. And this is the normal equation. Yeah? And this is how you find the W's. It's the x transpose x inverse times x transpose y. Now, this formula we can derive. And I made a separate video, which is optional, on how we get to this formula. Yeah? But it's interesting to see that, first of all, this inverse will not always exist. For example, if your x transpose x is singular, the inverse will not exist. So it happens quite a lot. So it's not always going to give you a solution. Sometimes it gives you unique solutions, sometimes it gives you many solutions, and sometimes it gives you no solution. Yeah. If you're not familiar with pseudo-inverse, inverse, and singular, take a look at my statistics refresher, and this is all explained. For example, if some of the columns in X transpose X are dependent on each other, then your chance is very real that X transpose X inverse does not exist.